Okay, so we've been doing some things with L'Hopital's rule, and we're going to continue talking about that. There's some other kinds of functions that we would have and things that we want to find the limit of that might be important. Before we go on, I just want to remind you a little bit about natural log of x. If we have the limit as x approaches 0 from the right of natural log of x, we want to think about the way the graph of natural log of x looks like. It's kind of like that. So as I approach 0, on the right side of 0, it is going towards negative infinity. And as I go towards infinity of natural log, it is going towards infinity. Also a reminder that natural log of e is 1. And so these all might be important to us as we are looking at some limits. Now, the first several problems are not really any different. It's just some things to talk about and things that you might have to do to find the limit. So I wanted to show you those first. On this one, it doesn't look like a fraction, so you can't just take the derivative of the top and bottom. But what we can do is we can rewrite it and make it a fraction because it has that negative power. And now that we have something that is a fraction, I can think about, okay, what happens when I plug in infinity? I do get infinity over infinity, so then I can find the derivative of the top and the bottom. Then I can think about, okay, that would be 1 over something really big, so that means that my limit is going to be 0. So you might have to manipulate the function just a little bit to make it work out easier. This is another example, secant of pi over 2 and secant squared of 3 pi over 2. I don't really know those that well. We could figure it out, but what I would do to make it easier is I would just go ahead and change it to sines or cosines because I think that's easier. So secant is 1 over cosine. I know that secant squared is 1 over cosine squared, so I'm just going to go ahead and change it to times and flip it. And so now we have a problem which is something we know more about. Not that we couldn't do secant, I just think that cosine is easier to look at. So now when I think of cosine of pi over 2, I'm thinking of, alright, I know that pi over 2 is over here, and this is negative 1, 0. Cosine's that, the negative 1. And so when I talk about, and you know what, that's pi, so I really need to be looking at pi over 2. This is 0, 1. Cosine is the x value, so this is 0. And then cosine of 3 pi over 2, it's still down here, so cosine's still going to be 0. Now we have 0 over 0, so now it's a problem we can use L'Hopital's rule for. And we want to find the derivative of the top and the bottom. The derivative of cosine is negative sine. Alright, the derivative of the top, I do need to use the chain rule, 2 cosine of 3x, and then the derivative of cosine of 3x is negative sine of 3x times 3. Nothing really cancels here, but now thinking about plugging in pi over 2, coming back to those coordinates there, sine of pi over 2 is going to be a 1. So I know that the bottom here is a negative 1. I know that this is going to be sine of 3 pi over 2, which would be negative 1. But we still have this cosine, which is 0, so we know we've got 0 times a bunch of stuff. And it's okay for our answer to be 0 as long as the bottom is not infinity. Okay, here's another trig one where you just have to sort of change some things around to make it work. And like I said, we could do it with looking at these, but I think it's much easier if you'll change it. Cosecant is 1 over sine. Cotangent is cosine over sine. Now we have something that we can just get a common denominator for, which is already a common denominator. So really we're just going to make it look like one fraction. Cosine of 0 is 1 and sine of 0 is 0, so we've got 0 over 0, which means L'Hopital's rule is appropriate. The derivative of the top would be, derivative of cosine's negative sine, we've got this other negative, that makes a positive sign. The derivative of sine is cosine. Plug in those zeros there, we have 0 over 1, so we get 0. Again, 0 is okay, and notice we got that on all three. Alright, there's some other examples we want to look at, and there's different forms that you might have with limits and using L'Hopital's rule. Another form would be something that when you plug in 0, you get infinity minus infinity. Now keep in mind, infinity minus infinity is not 0 necessarily. It might be, but it might not be. And so we have to do some things with L'Hopital's rule to figure out what that limit is going to be. So what you're going to do here is get a common denominator. Our common denominator is x squared. It's already there. If it wasn't, just make it, and then just make it into one fraction. Once we get a common denominator and make it into one fraction, then we can just solve it like we have been. So when we plug in 0 here, this would be 1 minus 1 over 0. So we've got 0 over 0. So we can go ahead and just do L'Hopital's rule. The derivative of top would be 3 sine of 3x. Derivative of the bottom would be 2x. Unfortunately, we still have 0 over 0, so we're going to do this again. I'm going to make it little to make it fit. But the derivative of 3 sine of 3x would be 9 cosine of 3x. Derivative of 2x would be 2. Now when we plug in our 0, cosine of 0 is 1, so we would have 9 halves. Alright, the next problem. When I plug in 0 here, 1 over 0, 1 over something small is infinity. Plugging in 0 here, that's 1 minus 1. Again, we've got infinity. That means that we need to get a common denominator. So our common denominator is just going to be x and then e to the x minus 1, which means on top I need to do e to x minus 1 there and minus x there. So then I'm going to, I guess I need to find out, can I use L'Hopital's rule? You can, because on top you've got 0 and on the bottom you've got 0. So the derivative on the top would be e to the x minus 1 because of that. On the bottom, we do need to do the product rule first, times the derivative of the second, plus the second times the derivative of the first. Alright, let's plug in 0 and see what happens. So e to the 0 is 1. Looks like we still have a 0 on the top. This would come out to be 0. Unfortunately, we've got 0 over 0 again. So we must do L'Hopital's rule again. Again, I'm going to try to fit it in here. The derivative of the top would be e to the x. Product rule again. First derivative of the second plus second derivative of the first, and then just the derivative of that would be another e to the x. Alright, on the top we have 1 now because e to the 0 is 1. This is 1, but times the x would be 0. So then we've got another 1 and another 1, so here we would get 1 half. Alright, number 6 we've already done. We did it previously. It was number 3, so we're just not going to do that one right now. Alright, number 7. So if we plug in 0, I don't even know what 1 over sine of 0. I was thinking infinity. That was not right. Sine of 0 is 0, so 1 over 0 is infinity. 1 over 0 again, so I know I need to get a common denominator, which is sine x, x times sine x. So the top, I'm going to multiply that one by x and this one by sine x. Alright, plug in 0. So now I have 0 over 0, so now I can use L'Hopital's rule. So 1 minus cosine over product rule first, derivative of the second, plus second derivative of the first. Yep, you guessed it, we still got 0 over 0, so we've got to do this again. The derivative of cosine is sine. Let's do the product first. Derivative of the second, plus second derivative of the first, and then the derivative of sine. We do have a 0 on the top, and then that'll be 0, but these are both 1, so 0 over 2, which is 0. Okay. Some other examples you might see. These two are just, or this last one's just a random example, but these three are problems like 0 times infinity. And I know we just want to make that 0 times infinity equal 0, but unfortunately it does not work that way, and so we'll work that out as well. What we want to do is, whenever it's times like that, is move one part of it and make it be a fraction. Okay? So what I want to do is rewrite this, leave the natural log of x where it is, but I want to make, instead of an x, I want to make it 1 over x, because now I've not changed the problem, I've just rewritten the problem, and so I can do that. And what will happen when you plug in 0, ln of 0, well, we know that's negative infinity looking at our graph originally, and then this is 1 over 0, which another is infinity again. So I know that now I can use L'Hopital's rule by rewriting it. So L'Hopital's rule says that I can find the derivative of the top and then the derivative of the bottom. Think of the bottom as x to the negative 1. So the derivative would be negative x to the negative 2. And I'm just going to go ahead and rewrite that because I think it's easier to solve. Now, you can go ahead and start plugging in zeros, and it looks like you got to do L'Hopital's rule again, but I would not suggest that at first. What I would do is I would change it to 1 over x times and then flip, because what happens is you get negative x. And then now, L'Hopital's rule is not required. So I would not plug it in when you've got fraction over fraction. Try to simplify if you can. Plug in 0, and we do get 0 for the limit. A lot of times when you see natural logs, that will happen. And 10 is similar, so I'm going to go ahead and do that one as well. What I would suggest, again, is to move just the x squared. I'd probably just leave the 2. You can move it to the bottom if you wanted to, but I think I would leave it like that. Think about plugging it in. You do get infinity on top and infinity on the bottom. The bottom is that whole fraction there, so 1 over 0 is infinity. Alright, and then so we want to use L'Hopital's rule, which means let's find the derivative. The derivative of the top will be 2 over x. The derivative of the bottom, think of that as x to the negative 2. So the derivative would be negative 2 over x to the third. I kind of skipped a step there, but if you want to write those steps, you can. Again, I would do like I did up here and flip and multiply, like simplify first. It does make it easier. You end up with negative x squared. Plug it in that 0, and we still get 0 for our answer. Okay. Number 9. So number 9 is a very similar problem. What we're going to do is we're going to take this x and move it to the bottom. So we're going to make it sine of pi over x over 1 over x. Alright, so here we have sine of pi over infinity. Well, pi over infinity is like 0. So sine of 0 is 0. 1 over infinity 0, we've got 0 over 0. So when I do the derivative here, the derivative of sine is cosine of pi over x times the derivative of pi over x. Okay, I'm going to think of that like pi x to the negative 1. So that would be negative pi x to the negative 2. And I'm just going to put it like that because I think that's easier just to look at. The derivative of 1 over x, that's x to the negative 1. So the derivative is negative 1 over x squared. Alright, I would simplify here before you start plugging things in. Negative 1 over x squared cancels with the negative 1 over x squared on top. So what I'm left with is negative pi cosine of pi over x. Alright, infinity goes here, so pi over infinity, that's the 0 in the limit. Cosine of 0 is 1 times negative pi, so that means negative pi is my answer. Alright, number 11. So this one's just a little bit different. I just wanted to share it with you. So you do have a 0 on the bottom. 0 here would be infinity, and then we have infinity here, so that's kind of weird. If this was the problem, then we would have to do some more things, but I will tell you this is supposed to be an infinity right here. So what that means is that this is infinity on the bottom, That's ln of infinity, which is infinity, and another one, so we've got infinity over infinity, so we're good. So I just wanted to talk about taking the derivative here. The derivative of natural log of something is 1 over the something, and then we multiply by the derivative of the something, and then over 1. And so at that point, instead of trying to do stuff, just go ahead and plug it in. 1 over infinity is 0. 1 over infinity is another 0, and so you get 0. I just wanted you to see how those derivatives related, and when you have a weird problem kind of like that. It's not really related to our section that we were working in. Okay, we've got one more section to look at. And in this section, it's examples like 1 to infinity, 0 to infinity, or 0 to the 0. These are ones, again, that we think we should know what they equal, but we do not. We don't always know that, so there's a process that we have to follow to work those out. So on our first problem, notice we've got a power here. Anytime that you have a power, what you're going to do first is rewrite it, and you're going to take a natural log. That's what you're going to do. So it's kind of like saying y equals this, and what we're going to do is we're going to take natural log of this side, and then we're also going to take natural log here. You can put it in front of the limit, but technically it just comes out like that. So what we're going to have is that natural log of y equals the limit. And when we put the natural log here, there's rules about natural log that this power comes in front of the natural log. So we really have this problem here. All right, I'm going to rewrite that. And I'm going to keep in mind that there's this natural log of y there that I will have to deal with at some point. I'm going to rewrite this as natural log of x over x because that's a problem we know how to solve. And when we plug in infinity, it's infinity over infinity. So I can take the derivative. The derivative of natural log is 1 over x. Derivative of x is just 1. So here we get that the limit is 0. However, that is not the answer because this natural log of y is still hanging out there. So I take natural log of y, set it equal to what I found, and then solve for y. You're going to rewrite it in exponential form. There's an understood e right here, and so you're going to get y equals e to the 0, which is 1, and then 1 is my final answer. So you have to put in a natural log, you have to bring the power down, and then you have to solve. Okay? So let's do that again on number 13. And this happens anytime that you have a power. Okay? So again, this is like a y equals, and we're going to put that natural log in front of it, which means we're going to have a natural log here. So it's going to give me natural log equals the limit as x approaches 0 of x, natural log of x. All right, this is one of those that are times, so I need to bring this x to the bottom. Remember that that natural log is there. But I'm going to bring it to the bottom and make it 1 over x. When I think about it, I do have infinity over infinity, so I can use L'Hopital's rule, which says that the derivative of ln of x is 1 over x, derivative of 1 over x is negative 1 over x squared. Okay, I can rewrite that. Then I can plug in my 0, so I still get 0, but 0 is not my answer because I still have this natural log of y hanging out. Understood e there, so y equals e to the 0, which is 1, and 1 is my final answer. Okay, we're going to do a couple more problems like that. Remember, this is y equals, so we're going to put that natural log in front, which means there'll be a natural log here. And that gives me 1 over x, natural log of e to the x plus x. That 1 over x comes in front of the natural log. This is on top. Plug in your 0, that is natural log of 1, which is 0. And then 0 on the bottom, so we have 0 over 0, so we can just find the derivative. The derivative of natural log of that would be 1 over e to the x plus x times the derivative of that, which is e to the x plus 1, over 1. Think about plugging in 0 here. So that would be e to the 0, which is 1. 1 plus 1 is 2. E to the 0 is 1 plus 0, so 1. So we get 2. That is not the answer there because we still have that natural log of y to deal with. And so y is e squared. Remember e, and you just rewrite it in exponential form. Okay, 15. Similar again. Natural log of y equals this, and put that natural log in front. And then we're going to put a 1 over x in front, which means there'll be an x on the bottom. Kind of the same as this, I just went ahead and put it on the bottom. Plug in 0. ln of 1 is 0, and the 0 on the bottom. So we're going to take some derivatives. The derivative of ln of that would be 2 over 1 plus 2x, because it's 1 over that times the derivative of that, over 1. And plugging in 0, again we get a 2 here. And so ln of y equals 2. Rewrite in exponential form, e to the second equals y. And that's my answer. Alright, 2 more problems, and then we'll be done. Nothing really different on these 2 problems, but I just wanted to make sure that you had seen them. So, natural log of y equals that with the natural log in front. My x will come in front. Because this is not a fraction yet, I do need to make that x go to the bottom to make it a fraction. Okay, plugging in infinity, that would be 0. ln of 1 is 0. 1 over infinity, that's 0, so 0 over 0. The derivative of natural log of something is 1 over the something, times the derivative of the inside, which would be negative 1 over x squared. The derivative of the bottom is also negative 1 over x squared. And I could manipulate this quite a bit, but notice that this is on top and this is on the bottom. You can just cancel those. You're left with 1 over 1 plus 1 over x. Plug in infinity. This would be 0. So you've got 1 over 1, which means the natural log of y equals 1. There's an e there, so y equals e to the 1, or just e. Okay, 1 more problem. Natural log of y equals that with a natural log in front. Go ahead and bring our 1 over x down, which means there'll be an x on the bottom. Plug in 0. That's again natural log of 1, which is 0 over 0. Find the derivative. The derivative of natural log of something is 1 over the something. Times the derivative of that, and that looks like I've already done this problem in number 14. So I'll just go ahead and tell you it was y equals e squared. I did not realize we had the same problem there, so we don't have to finish that.